Good evening, folks. It is about 5 minutes until the Day 17 puzzles for Advent of Code unlock. Very exciting times. So last night, we solved the Day 16 puzzles. I just wanted to cover a little bit of an update I made to our solution since the last stream. And that was that previously in this find order impl where we had used a flat hash map to store the mapping of rule positions to the actual rules. I just changed that to a vector because I realized, it'd be a dense range. We're trying to fill in, exactly rules 0 to 20. And so, I just made that a vector that is exactly sized for the rules. Initially filled those with null pointers, and then just put pointers to the respective rules in those when we assign them. And so that's just a little bit of a simpler data structure, probably a little bit more efficient. And those changes have now been uploaded to the GitHub repo. As always, if you're interested in seeing the code, it is up in my GitHub repo. I'll put that on the screen now. That's github.com/craig-chasser/AOC2020. You can always find the code there. And there is a link down in the description for the stream to that GitHub repo. If you're watching this on Twitch, there should also be a link to my YouTube profile where you can always watch the stream replays on my channel. Conversely, if you're watching a replay on YouTube, there's a link to my Twitch channel, which has our nightly live streams starting just a little before 9 p.m. Pacific time each night, midnight Eastern time, or, I trust you to do the math to convert to your local time zone. So we have just a couple of minutes before tonight's puzzle unlocks. In that time, why don't we get just a little bit of a head start and make the directory for our new puzzle, for our new day of puzzles, day 17. And we will make our little minimal C++ program for part 1. You've seen me do this many times by this point. Okay, there's our minimal program. And we'll make a build file so that the Bazel build system that I'm using knows how to build it. Okay. And let's just try and compile and run that little program to make sure that everything is working okay. Okay. And it compiles and runs and does nothing, just exits, which is what we expect. Let's go ahead and include a couple of the util libraries that I have set up here. For check, which is what I use to just do assertions, and the IO library that I use to read in our file input, because we're probably going to need both of those. We've needed those for almost every day's puzzles. And we'll go ahead and put the dependencies in for that. Okay. Once again, compile and run. And we are all set to go. As always, if you have any questions, feel free to ask them in the chat, or if you're watching the replay on YouTube, feel free to ask them in the comments, and I'll do my best to answer you. We have just a few more seconds until tonight's puzzle unlocks. All right, day 17. What do we got? Conway cubes. Ooh, does it involve Conway's Game of Life, maybe? As your flight lasers through sky, elves from the North Pole contact you. Debugging an experimental energy source aboard a super secret imaging satellite. Seeing who's naughty and nice. Have an infinite 3D grid. Integer dimensional coordinates x, y, and z. And each cube is either active or inactive. Okay, so we've got like a three-dimensional game of life, it seems like. Okay. Each cube only ever considers its neighbors. Any of the 26 cubes where their coordinates differ by at most 1. Okay. So it seems like there'd be, yeah, 9 above, 9 below, and 8 around that are off by at most 1. Okay. If a cube is active and exactly 2 or 3 neighbors are also active, otherwise it becomes inactive. Cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active, otherwise the cube becomes inactive. Okay. Even though a pocket dimension is 3-dimensional, this represents a 2D slice. Okay. Yeah. So we have a 3D cellular automata here. And we just need to simulate Conway's game of life in it. So, as for a data structure that we could use, I think it is very tempting to just say, oh, we have a 3-dimensional space, we should have a 3-dimensional array. But the space needs to be able to grow arbitrarily because we have an infinite space, so we're going to be simulating more and more of it. I kind of feel like the way that we want to approach this might be to just, at least initially, have a sparse representation where we just store the coordinates of all of the active cubes, and then, you know, store them in like in a lookup structure like a hash map. So that is the approach that I'm going to choose to take, although I think that, you know, actually having a grid, totally valid way to approach this as well. But I'm choosing to have a sparse representation. So let's just have a coordinate struct that has x, y, and z. And we want to make this struct so that it supports hashing inequality, and we can use it as the key in a hash-based container. So using the Absal hashing framework, it's pretty easy to make a type hashable. We just kind of have to follow this recipe here. So we have a template, type name h, that represents the hash function, and then this special Absal hash value method, or actually it's a friend function, really, it's a free function, but so you have h to represent the state of the hash, we pass in those coordinates, and then we do return h combine, move the state of the hash, and then the additional arguments to h.combine are just the additional fields, the primitive fields that we want to mix into the hash. No, that seems a little complicated, but basically this is just a simple recipe that you can follow to make your own types hashable in the Absal framework. And so we're definitely going to want to include flat hash set as well. Okay. And we also need this to support equality comparison, because that will also be used in the container when we're looking up coordinates by their hashes. So we just make sure that all of the x, y, and z are equal. Okay. The next thing that we'll do is we will have a class that represents the state of our infinite grid. Now in here, we're going to have a flat hash set of these coords that represents the active cubes, the active Conway cubes in our infinite grid. So first thing that we're going to need to be able to do is parse the initial state of the grid from our text-based input. So we will have just have our constructor do that from a vector of strings. And so z is always going to be 0 for these, and then we can just go through x and y. So we'll say, for y, well, so if that particular character is active, it will be the pound sign, and we will add an element to the set. So that will be coords with x equal to the x value, y equal to the y value, and in this case, we're always starting from just one level of the grid, so z will always be 0 there. And then always increment x in this inner loop and increment y in this outer loop. And that should give us our initial state. So then we just need to write a method that simulates one iteration of this game of life and gets us our next active, so advances the state, it advances the time by 1. Or by n, but we can just call it repeatedly. So we'll just say we'll just call this method step. And what we will do here is, so each cube only ever considers its neighbors. So the rule here is if a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active, otherwise it becomes inactive. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active, otherwise the cube remains inactive. So the only coordinates that we need to consider are the active cells, the active cubes, and those coordinates that are just 1 away from the active ones in any direction. So what we can do here is I'm going to make another little method, and chords is getting, somewhat more and more complicated, and maybe shouldn't even be a struct anymore. Maybe it should be a class, but I'm going to keep it just for now, because I'm going to add this method here that returns a vector of what we will call adjacent and self. And this is just going to give us all of the coordinates that are either adjacent to this one or that are this this cell itself. So it lets us know all that we have to consider for a given active cell. And as we're doing this for multiple active cubes, if we're processing everything from the adjacent and self list for each of them, we'll process some things twice or more, but that's okay because we'll always get the same result of the computation each time. So we might waste a little bit of time, but it's fine. So what we want to do here is just we will reserve 27 because that's exactly how many there will be. And actually, you know what? We're going to want one for adjacent and then one for adjacent and self. So we'll say and even though if we're just using adjacent for this, there's only going to be 26 elements, I'm going to put one extra in there because sometimes we're going to throw self into the computation for something else. So we'll just say for possible delta x, difference in x, -1, 0, or 1. Similarly for delta y and delta z. We will, if any one of these is if any one of these deltas is non-zero, it means it will be a different cell. So we will just fill in the fields by adding this particular coords with the delta for each coordinate. And then just return that adjacent set. So what we want to do in this step function is look at well, so we also want to maybe count adjacent. There's a lot of ways we can optimize this computation, but I'm not super worried about that right now, about wasting too much. Maybe I will at some point. Yeah, because this state is not too crazy complicated, and even if we do simulate it 6 cycles, I really don't think it's going to get too out of control. So So we can count the adjacent for the chords. So we'll just say for each of the adjacent set of coordinates for a particular cube, we check if it's in the active set, and then we increment the adjacent count if it is, otherwise we don't. So now, getting back to our step function, we will say for each active cube in that active set. Well, so first thing we'll do is we'll have next active, where we'll store all the results of these computations. But for each active cube, if the cube is active and exactly 2 or 3 of its neighbors are also active, it remains active. Otherwise, the cube becomes inactive. So we'll say, so if we'll actually maybe make another helper method here. So we'll say bool both of these can be const qualified, I realize now. So if a set of coordinates is currently active, so if active dot contains that set of coordinates, then it stays active if exactly 2 or 3 adjacent cells are active. So for this we return neighbors active is exactly equal to 2 or 3. Otherwise, the cube was initially inactive, and it becomes active only if neighbors active is exactly 3. So we will say if next active for that particular active cube is, if that is true, then we will put it in the set of next active cubes. So we'll say next active dot insert that particular active cube. And we'll do the same for all of its adjacent cells. Now, remember I said that it's definitely possible that we will be computing the results for the same cells multiple times because they can be adjacent to multiple active cubes. That's okay because the result of the computation is always going to be the same. We might waste a little time, but the result will still be correct. So let's say for all of the ones that are adjacent to active cube to the active cube, we're going to do the same thing. So and then we will just, at the end of this, where we have figured out all of the cells that are going to be active in the next iteration, we will replace that active map with the next version of it. So we're going to step a certain number of times. It looks like 6 times. And then the final answer that we need to get is to count up the number of active cubes in the final cycle. So that is actually pretty easy to do. It's just the size of that set. So I think... So then all we have to do... I think we have all of our logic now. We just need to do the I/O. So we'll do a check here to make sure that the count of arguments is 2, because one of the arguments we expect is a file input. We will read that vector of strings that is the initial state of our map. We will make our grid from those lines. We will step it forward 6 times. And then we will spit out the number of active cells in the grid. So the only additional dependency we need here is flat hash set, it looks like. Put that in our build file. And just as a test, we will use that tiny sample input that was given on the website. So I'll just paste that over here. And now let's try and run our program with that test input. There was a check failure in I/O. Interesting. Well, that shouldn't happen. Try that one more time. Oh, it should be argv1. Yeah. A little off by 1 there. Okay, so that gives us 112, which the website says is correct. Let's simulate it for our actual test input for day 17. We've got 232 active cells. Let's see if we're correct. Hello in chat. 232. Bingo! Oh, and we're in the top 1,000. Rock on for us. For some reason, your simulated results don't match what they expected. Apparently, Pocket Dimension actually has 4 spatial dimensions, not 3. Okay. Hypercubes. All right. So we are extending this to 1 more dimension. I will copy. I'm going to go ahead and copy our day 1 solution just to get this started. But actually, I'll keep the screen over here because I want to read up on this more. But just doing that here. Okay. So we have 1 more dimension. Get into W space. Okay. We just extend this to 4 dimensions. This is not... I don't actually think this is all that hard. Let's see how fast we can do it. So we add I'm just going to add a W dimension to everything. Now, if I had made this fully general, I would have, instead of having, these dimensions be named, I would just, make, everything totally general in its dimensions. But honestly, this is still not totally out of control, even with the W dimension. Adjacent.reserve. We never really use that additional one, but we should reserve 80 here. And then we'll have delta W. Need to put in a condition for delta W. This is almost mechanical at this point, just adding in one more dimension into all of our data structures. Dot W equals W plus delta W. So that gives our set of adjacents. We're always going to be at W equals 0 in the fourth spatial dimension. Num active, next active. This is all going to be the same. We've just added the additional dimension to our representation of coordinates. So we might actually have our part 2 ready to go here. I'm going to set up a build target for it. I'm going to run it on the initial test input. Okay, it's taken a little more time, but it got 848, which is the correct result. Let's see how it does. Now this is, maybe the grid gets so big that, things should be more efficient now, but I'm going to let that chug for just, okay. That only took a few seconds. Let's see if 1620 is correct for our puzzle input. I feel pretty good about this. 1620? All right! 715 did even better on that leaderboard. So this was fun. I think we got a little bit lucky this evening in that I happened to choose a representation for this, for the data structure, that made it really easy to extend to one more dimension, because the sparse representation that we had, where I just put everything in this flat hash set, all these sets of coordinates, it made it so we barely had to change grid at all. All the logic for figuring out the next iteration, for counting adjacent cells, for counting the next actor and everything, that all worked exactly the same. We only needed to change coords so that we put one more field in, and we consider that when we're generating all the adjacent coordinates, and all the logic works the same with one more dimension. So I'm actually really glad that I chose that sparse representation instead of trying to, make up a 3D grid. I mean, extending a 3D grid to 4D wouldn't have been, beyond the realm of possibility. Totally could have done it, but just having a little bit of smartness in this chord struct was really, really advantageous to us. So, yeah, this was a fun one, playing Conway's Game of Life in 4 dimensions. But yeah, that's our solution for this evening. I had a lot of fun. I hope we all learned something. I think, one cool thing that we showed here is adding, just making a custom type usable in the absol hash-base containers. You just need to do this absol hash value function and provide the equality operator, and then you can just use that in flat hash set or flat hash map. So it makes it really easy to make composite types like coords fit in with these cool containers. But yeah, I'm very satisfied with the solution. I think that we happen to have found something that really shows the strengths of a particular design in C++, which is, kind of separation of concerns between algorithms and data, because the grid implements the algorithm for figuring out, the next state of itself, but the coords struct, is responsible for figuring out what's actually adjacent to itself. And that separation of concerns worked out marvelously when we moved on from part 1 to part 2. So that's about it for this evening. I want to thank everyone for watching. Thank you for watching the live stream on Twitch. If you're watching the replay later on YouTube, thank you for watching there. You can always find links to my GitHub repository where all this code goes down in the description. Links to the YouTube stream replays or the Twitch live streams also down in the description. Again, if you have any questions, feel free to leave comments. I will do my best to answer them. Thank you so much for joining me tonight for this puzzle. I look forward to seeing you again tomorrow night for day 18. Bye-bye, everyone.